Hey guys, you're watching Python tutorials on my YouTube channel, Python for Microscopists. In the last tutorial, I talked about what regression is and what binary classification, multi-class classification, and multi-label classifications are, and promised to actually provide you individual videos on these topics. And here is the first one of that series. And this one's about regression using neural networks. Very shallow neural networks, but still neural networks using the dense layers. Okay, and I'm going to stick with Keras library for this. And what fun is just doing this in neural networks and not comparing this with other models that we are familiar with, like linear regression, decision tree, and random forest. So we're going to go ahead and do that, okay? So, and for this, the data set I'm going to use is the Boston housing data set. Again, if you're not familiar with that data set, this is basically a CSV file, okay? And let me show you a CSV file, but not comma separated. This is space separated, okay? The file that I have. So instead of comma, let's actually add a flag for space, but otherwise this should have about 14 columns. And each column, unfortunately, they are not labeled here, but I have a separate document that actually tells us what the labels are. So first column is per capita crime rate by town. So obviously you can imagine that the housing prices are very much dependent on the crime rate, but how much of that is dependent we don't know, but we'll see if we can model those. Now there are a whole bunch of other I don't even know why they have this nitric oxide concentration per part 10 million. I didn't even ask that question when I was purchasing my house, so apparently that's a factor. Average number of rooms obviously makes sense, but if you look at the last value here, MEDV, it says median value of owner occupied homes in 1000s. That's nothing but price of the house, okay? So that's the median price, but the price of the house. So for each entry, this is what we are trying to predict. Yeah, so this is the label in our case. So the first 13 are the features, and the 14 is what we are trying to predict, or what we are trying to use to model our data set so we can predict that in future. Okay, so we can actually rename this to price for intuitive thinking. Okay, so this is the data, and I'll provide this, I'll make this available on my GitHub page, so don't worry about it. Now let's get to the code. As usual, we start by importing the right libraries. Again, I'm not going to type the code right now and waste your time and my time while we do this, but I've written all these lines of code beforehand, so we can just go through this. Okay, I'll make the code available anyway, so don't worry. So let's go ahead and run these lines. And again, as you can see, I'm importing pandas because that's a great library to handle data. And everything else should be very straightforward. And scikit-learn actually has a lot of good tools, especially for traditional machine learning. If you want to do random forest or just trees, or even quantify like the accuracy, like looking at cross-validation scores and so on, it's got like very useful tools. And we are going to, of course, so we are very much used to train, test, and split to actually split our data set into training and testing data sets, right? Okay, so now let's start by loading the data, and I'm using pandas. I'm creating a data frame, okay, and I'm using read CSV from pandas to read my CSV file, and here I added my delimiter as white space and not comma, okay? I just put that as true, and everything else is, we don't have a header, so I put header equals to none. Otherwise, it thinks the first row is header, okay? And let's go ahead and run this line so we can see exactly what we have. So if I open this data frame, so here it is. So the data frame is right there. Okay, so we have all the values loaded. Now we don't have the column names, so I took time to actually look at this and then add a an array with all of these values. So when I run this, now we should have a list, basically, not an array. I didn't convert this to a NumPy array or anything. So this is a list with 14 feature names. Yeah, that's what I call this, feature names. And now what do? After we have this list, now I'm going to add these list as the column names, right? So the way we do that is our data frame dot columns. Okay, again, please watch my pandas tutorial if you want to know more about this. So now it's printing this. I can open my data frame again. Now you see how you have all the columns up there, column names, including our median value. Okay, so our data is ready basically, except like I mentioned, I don't like the name MEDV, so I'm going to replace that by putting price there. Again, I try to include a couple sub tutorials as part of master tutorial. So here is a small tutorial about how to handle data in pandas. Anyway, so let's go ahead and run these, and let's also describe our data. You know what describe actually does? You can see from the output here. Okay, so the describe provides a quick view of all the statistics. So you can see that, okay, for my price, there are 506. All of these should be 506, right? Because there are 506 data points. But my mean is 22, my standard deviation, and all that stuff. So this gives a great snapshot of how the data looks like. Okay, now let's get back to the code. So now we have that. Now let's define our features and the label, what we're trying to predict. Okay, the features are every column except for the price. Price is not a feature. Price is what we are trying to predict. So let's drop the price, and axis equals to 1 means the column. Okay, so let's run this, and now you should see an X where you have everything except for our price. Okay, now our Y is exactly opposite. Our Y is basically the price column. Okay, so this is our Y. So if I open my Y, you'll see that, okay, this is a price with all the price. That's it. If you think about this in a methodical way, this is as easy as it can get. Okay, so the next step is, again, remember we imported the train test split. So I'm going to split our data set into the training and testing for X, training and testing for Y, and the inputs are obviously X and Y. And the test size is 0.2. That means 20% of the data will be assigned to the test. And I fixed random state equals to 20. That means every time I run the code, I get the same split. So I can compare the results if I'm doing some experiments with this data. Okay, so let's go ahead and run this line. So there you go. So now we have our X test, X train, and out of all 506 data points, 404 belong to our training data set, and 102 belongs to our testing data set. Okay, so we're all set to actually go in, but one thing, if you have watched again the last 3-4 tutorials, I did talk about scaling the data. If you look at this data, if you look at this, some of these have a mean of 3.6, some have a mean of 11.3, some have a mean of 22, and if you look at others, the values range quite a bit. So when you're trying to model this, then the model can be a bit biased towards the heavy high numbers. So to bring everything to the same level, we have to normalize them. You can either divide every one of these value by the maximum value within that specific category, or scikit-learn preprocessing has something called standard scaler. You can use this to scale all the values to certain numbers. So that's what the standard scaler actually does. Okay, so here I'm doing the X-train and X-test scaling. So when I run this, let's go ahead and run these. And if I actually open my, let's say, X-test scaled, now you see all my values. Now let's just open X-test. So on the right-hand side, unscaled. So you have values 15, 19, and so on. On the left-hand side, these are all scaled. Again, these are not scaled to between 0 to 1. This is a different way of scaling by using standard scaler. Again, please look at the documentation for scikit-learn preprocessing standard scaler to see exactly what they're trying to do. Okay, but either way, the whole point of this exercise is to scale the values to bring everything into one normalized space or one scaled space. Now here we are getting into defining our neural network, and again, because all of my values are one-dimensional, this is not a two-dimensional image. If I have images, then I like to add convolutional layers. Okay, that's because it really helps to have the context of or leverage the 2D arrangement of the pixels. For one-dimensional convolutions, usually they don't matter much. So I'm going to only use the dense layers as part of our neural network. Again, I hope you know what I'm talking about. In neural network, you have convolutional layers, you have dense layers, right? So the convolutional layers are very useful for image processing type of applications. Even for others, they are definitely useful, but dense layers is where you have these dense connectivity, hence they're called dense layers. Again, please watch my earlier videos on the topic. So I'm using two dense layers that are hidden. One is with 128 nodes, 64, and our input dimensions is 13, right? We had 14 initially. One is assigned for our label, so we have 13. And I'm going to use ReLU activation, which is fine. Again, try different activations, okay? I'm going to use ReLU, but you can try like your sigmoid or some other activations to see how it affects the model. Now, the final output layer, again, the dense layer, of course, it has to be a value of 1, right? Because we have only one output, which is what is the final value, okay, after it goes through all of these dense layers. So this is the output, and again, this number has to equal to the number of outputs that you're trying to predict, in this case only 1. And my activation, I'm going to use linear. Again, this is something you can try using your own. Finally, I'm compiling the model using what loss function? Mean squared error function. Again, for regression type of problems, mean squared error works great. And optimizer, I'm using Adam optimizer. Again, you can try different optimizers, but Adam is okay. And what metrics am I going to keep track of as I'm training this model? Mean absolute error. So I can plot it later, okay? So this is, again, not crucial, but this is something useful. And we can define our model.summary. So let's go ahead and run these lines so you can see exactly what the summary is. So I have here 1,792 parameters that it learns at this point, and then 8256, so total 10,113 parameters. And finally, it gives me an output of 1, okay? Hopefully that's not new to you guys. And now let's go ahead and model.fit. We are here fitting the model on what? On our X trained training data set that is scaled and Y train, okay? This invalidation split is 0.2, okay? And epochs is 100. So let's go ahead and train. So this should be pretty quick because this is just a couple of dense layers with very minimal amount of data. So you can see our mean absolute error jumping up and down over there. But let's look at the final curve to see how it actually looks like. So for now, let's go ahead and plot these. What are we plotting? The loss and validation loss and mean absolute error. Remember, we are tracking the mean absolute error. That's the reason we can actually plot those. And let's do that both for training and testing data sets. So let's run these lines. I always have these two in all of my code, any neural networks or even otherwise. I have these so I can actually see how fast the learning goes. Again, this is, I think, a pretty simple, straightforward problem. So as you can see, it converges pretty fast. I don't even need 100 of these epochs. Maybe even 20 is more than enough, okay? So this is our training loss, and this is our training and validation mean absolute error, okay? And am I printing out anything else? Let's go ahead and print a few. Let's actually predict on some test data. So here what I'm doing is taking the X train instead of model.predict on train. I could have actually selected test, not train, but that's okay. Let's, in fact, let's change that X test and Y test, okay? So I'm actually grabbing the first 5 entries from the testing data set, and then from, in X and Y, and I'm just doing the predictions on those. So let's go ahead and run these to see how the predicted values are. So the predicted value for the first one, 18.37, the real value is 21.2. Next one, 20.18, 20.6. 19.8, 21.5, 20.4, 21, 13.07, 13.4. Not bad, actually. That's pretty close. Okay, so as you can see, this is what regression is. You're actually predicting the actual value down to a decimal point, but obviously it depends on the accuracy whether that decimal is needed or not. So that is how you do this with neural networks, but let's actually compare this with other models. And what metric shall we use to compare with other models? The easiest one is mean squared error and mean absolute error. Let's actually print out these two. Okay, so and because we already have this neural network model, the way you do that is model.evaluate. When you run that on your test data set, it automatically gives you 2 outputs, which is one is MSE and the other one is MAE, mean squared error and mean absolute error. So let's run this and have a quick look at this number. Okay, so here. So the error from neural network, mean squared error, is 14.95 and mean absolute error is 2.88. Okay, now let's see how linear regression compares to this. Okay, is the error higher or lower? Okay, I don't know what to do with these numbers. Well, you can compare with the original values and all that, but let's compare against other models. Now for linear regression, again, I hope you looked at my tutorial about linear regression. This is very simple again. First, I'm actually importing all the libraries I need. I'm going to do decision tree later on, so I imported that. I'm also going to import linear model from scikit-learn, and from the metrics, I'm importing mean squared error and mean absolute error because these are the two that we need to calculate. Okay, so now let's create some space here. Okay, linear regression. So the way you do that is create a model instance, right? Linear model dot linear regression, and then fit that model onto your train scaled data, and then y-train, right? This is exactly what we have done for neural networks, except here our model is linear regression and not neural networks. And once it's there, we are going to do our prediction on X test. Let me make sure. I tend to confuse or mix test and train. But okay, this seems to be good. Then we are predicting all the y values on our test scaled data set. Did we do test scaled here? Yeah. And then we are calculating mean squared error and mean absolute error. So that should do. Let's go ahead and run this. Linear model is not defined. Of course it's not, because I haven't executed those lines of code. Okay, so here my mean squared error is 16.49, mean absolute error is 3.05. What did we have from neural networks? We had values of 14.95, 2.88. So this is not as good as neural networks. Typically, neural networks works very well. The only thing from traditional machine learning point of view that I absolutely love is random forest. I think in most cases it beats neural network because we can do some feature engineering with that. But let's not get into that discussion for now. So now let's actually look at decision tree. Again, this is not random forest, but a regular decision tree, one decision tree, right? This is not a forest, a decision tree. Let's go ahead and run this. Again, very similar to linear regression, except I'm creating an instance for decision tree regressor and then applying that and then calculating these, okay? Mean squared error and mean absolute error. Okay, so what did we get? This is worse than linear regression. So now we have 18.68 and 3.08, okay? And with our neural networks, we got 14 and 2 point something. So now let's get down to random forest. I love random forest, like I said. Let's actually give 10 estimators, which means it's actually doing 10 trees, let's say, okay? So let's go ahead and print out. Again, I'm creating this random. By the way, random forest has two things. Scikit-learn has two variations of random forest. One's called random forest regressor, which is useful for this type of application. The other one is called random forest classifier, obviously used for classification. So I'm going to use regressor here, and I'm going to, everything else is self-explanatory, exactly what I've done before, okay? So let's go ahead and run this to have a look at the output. So this is not great. I mean, it's better than using decision trees. You see, 15.21. 2.57, also better than linear regression, but it's not better than our neural networks, where we got 14.95 and 2.88. 14.95, 2.88. Yeah, slightly better in terms of mean absolute error, but let's do the trick of adding more trees. 30. By the way, if you add even more, then it gets worse, okay? So there seems to be a balance, but let's actually change this to 30 trees and then see if it gets better. There you go. You see how you got 12.25, 2.38. So that's why I absolutely love random forest for most of these type of regression problems and also classification if you can engineer your features, okay? But meaning in this example, we already have our features, okay? So this can be a great way. Now, one other thing that's also useful when it comes to random forest is it can actually give you feature ranking. Again, I'm not going to go through this code. You can go through it yourself when you find it on GitHub. But when I print it out, it tells you which of these parameters, which of these features contributed the most towards the decision. which is absolutely, this is what I do not like about neural networks and deep learning. It's very difficult to understand why it worked. Yeah, it works, but it's difficult to understand why it worked. With random forest, it tells you why it worked. It's like, hey, it worked because the weight for L stat, whatever that is, and RM is between these two, they seem to be the biggest decision makers. So what is L stat and RM? L stat and RM. L stat is percent lower status of the population. So obviously, if you have lower status of population, the pricing is lower, which is obviously understandable, right? And you have these poor neighborhoods and rich neighborhoods, so it kind of makes sense. And the other one I totally forgot. Sorry. RM stands for average number of rooms per dwelling. Of course, if you have more rooms, the house is going to be more expensive. This is this is the beauty of random forest. Again, I don't want to make this video a random forest evangelical messaging video, but you can see why I prefer that over deep learning for most of the time. Deep learning is great, if you have a lot of data and challenging problems, but for something that's straightforward and simple, give random forest a try. But this is how you do things with, this is what regression is, whether you end up using neural networks or random forest, but regression is predicting a value, a specific value, and not categorizing it. In the next tutorial, let's actually start looking at classification and labeling problems, okay? So thank you very much. And again, as usual, I hope you liked this video, and hopefully you watched this in its entirety. If there are any boring parts, let me know if I talk too much, so I can kind of make these videos better for you guys. So anyway, please go ahead and subscribe them, and thank you very much for your attention.